Lecture 14, functions and sets, so we're going to carry on saying a bit more about functions. There's two new handouts today, and I've got spares from last Friday. The spares are here in this box at the front. Now we're going to start with something a bit different, because although I gave you an abstract definition of function last time, most of the functions you've actually met have been the values your functions have taken have usually been real numbers, maybe sometimes complex numbers. Maybe occasionally you've had functions where the value was a vector or something like that. But you haven't usually dealt with functions where the value the function takes is something strange like a set. Okay? So I'm going to just give you a few examples of functions where the values taken by the function are actually your functions the values taken by your function could be any sort of mathematical object, really. In particular, sets are perfectly good objects, and so you're allowed to have f of x is the natural numbers, or f of y is the set of rational numbers, or something like that. And that's the sort of thing I'm just going to show you now. Okay, so. Yes, the function has to map each element of the domain to exactly one element of the codomain, whatever function you've got, but the things in the codomain can be strange. And the codomain could be a set of sets, in which case every value taken by the function will be one of those elements of the set of sets. So, notation here, the power set of a set, p of x, also 2 to the x, it's a set of all subsets of x. And another thing we did before was we had sometimes an equivalence relation, and then we looked at the equivalence class of x. That was those things that were related to x. So the equivalence class of x is a set. So you take an x in your set x, and you've got some equivalence relation. For each x, you write this square brackets x. Square brackets x is no longer an element of x. Square brackets x is a set of elements of x, namely those y in x which are related to x, the equivalence class of x. And that is already an example of a function that takes whose values are sets, because for each x, this square bracket x is a set of elements. And so if you take the map that takes x to its equivalence class, that's a set-valued function. Okay, so here are some set-valued functions, right? This one's a bit odd, the first one. This takes real numbers, and for each real number you get a subset of the real numbers. However, it's a rather boring subset of the real numbers. For each x, I take it to a single set subset of R. So that's a single point subset. Remember, x is not the same thing as the set which has just got x in it. Right? So x is a real number. This set which has just got x in it it's a subset of the real numbers which has got one point in. So, for example, f1 of 3 is a set. It's a set which has only got one element in, and the element in that set is 3. That wasn't very well written. I'll just try that again. It's a set which has just got 3 in it and nothing else. Three is a real number. The set which has just got 3 in it is a subset of the real numbers. Now, here's another one. Natural numbers. For each positive integer n, you can look at the set minus infinity n. We did this sort of thing before when we were looking at indexed families of sets, and we were taking their unions. So again, this time the value f2 of something is going to be an interval. So f2 of 4 is equal to the set minus infinity up to 4. 4 is a positive integer. This is a rather nice subset of the real numbers. The third one here, these are basically things called Dedekind cuts. You probably won't ever see a formal construction of the real numbers, but suppose you know about the rational numbers and you're wondering what the real numbers are. One way to approach figuring out what the real numbers might actually be in terms of the rational numbers is to use things called Dedekind cuts. And here are some. For each real number, you take the set of rational numbers which is strictly less than that real number t. So it's slightly different from the one before. f3 of root 2 is equal to q intersected with the interval from minus infinity up to root 2. So you start with a real number. The new thing is a set of rational numbers. Now the nice thing is that you can, if you know what this set of rational numbers is, you can figure out what the real number has to be. If you know what the real number is, you can figure out what the set of rational numbers has to be. So although these things are subsets of the rational numbers, you could use them to describe all the real numbers this way. So that's one approach to finding the real numbers. Okay, and then this one here is a special case of the one I mentioned before. This one is you look at the set of all odd integers and the set of all even integers, and if you remember, those form a partition of z. So they give you a partition of z into the odd integers and the even integers. And you can now say, for each integer n, the set I'm going to take is the corresponding set. So if n is odd, I'll take the set of all odd integers. If n is even, I'll take the set of all even integers. And that's actually a special case of the one I mentioned earlier, where you map something to its equivalence class, because this is the equivalence classes you get when you do congruence modulo 2. So if you're using congruence modulo 2, and you say, let's map, let's my function be defined for each n, I'll go to the equivalence class of n, this is what you get. And you can do that for any other equivalence relation as well. And this is quite nice, actually. It's quite a useful construction when you're trying to work in topology or something like that, because you quite often want to, if you've got something, some topological shape, and you want to talk about what does it mean to say glue the sides of this piece of paper together. A typical thing you might do is you might take a sort of square or rectangle and say, okay, I want to glue these corresponding sides to each other. If you do that, that's like folding round the piece of paper and now you've got the surface of a cylinder. But then you say, and now I want to glue the top edge to the bottom edge. And that means, oh, that didn't work very well. I'm going to have to recalibrate this screen. So now you glue the points on the top edge to the points on the bottom edge in the same way. So what you do is you take your cylindrical surface and you wrap it around itself and you make the surface of a donut. And that's a typical thing mathematicians do in topology. And how do you do it? Well, what does gluing together mean? It normally means you form an equivalence relation where you say the points on the top are equivalent to the corresponding points on the bottom. And the things on the left side are equivalent to the corresponding points on the right side, and everything else you leave in peace. When you do that, the equivalence classes tell you which things were we putting together, and when you quotient out by the equivalence class, it's how you glue the points together mathematically. And here is the quotient map. So what does it do? You take an equivalence relation on X, and Q for quotient map takes X to the set of subsets of X by each X goes to its equivalence class. Now, if this was congruence modulo 10, then you'd have just 10 points. You start with the integers, and you now have sort of 10 equivalence classes corresponding to what you have remainder modulo 10, and you'd be taking the whole of the integers and mapping down to 10 points corresponding to what the remainders were. If you start with this square or rectangle and you do the equivalence relation that says what I said before, then you effectively end up with a torus, the surface of a donut. Okay, that's all I'm going to say about that for the moment, but just to show you that functions can take interesting values, and they've got, when you go further down mathematics, all of these kinds of functions have got important applications. And we will see some things today which are really set-valued functions, though we might cover up that fact. Right, so, okay, so let's look at images of sets under functions. So this is what was probably called range in calculus. And when you look at all the values that your function can take. So we'll start with the function f of x equals x squared defined on the whole real line, taking values in the real line. And you ask, what are the values this can take? Well, we know that you only get non-negative real numbers, and you can get all the non-negative real numbers this way. So when you look at all the values you can get, f of x, where x is in R, and our notation for this is going to be, it's going to be called, this is going to be called the image of f, and we're going to write it as f of R, is a set of all the values you can get at. And by the way, you maybe have somewhere squirreled away, I gave you a set of notation for working with functions, and all this stuff is on the notation sheet for functions. So I've given you 2 notation sheets. If you've lost either of them, you can get them from the Moodle page. So don't forget, your 2 notation sheets should be quite useful. So the image of the function, f of r, that's the set of all things you can get to, f of x, so x is in R. This is the same thing. Those real numbers are which you can get at by something from somewhere. And in this case, we know what you get is all the non-negative real numbers. But if you restrict attention to 1, 2, this one, we denote this one. This is the image of the set 1, 2. Not an ordered pair. This is the interval 1, 2. It's a set of all things you can get to if you start in the open interval 1, 2, and you square. Or the set of real numbers where there's something in 1, 2, which when you square it, you get y, which is just 1, 4, okay? So if you square everything that's strictly between 1 and 2, you get the real number strictly between 1 and 4, so that's easy enough to check. And these are examples of images of sets under the function f. So this one is the image of the set 1, 2 under the function f. So this one isn't the range of the function because you just saw what it did on a particular subset. The top one, where you applied it to the whole of the domain, is what I think you call the range of f in calculus. I avoid the word range because of a clash with what they do in Cambridge, but called the range of f in D11 Cal. You apply it to the whole of the codomain and see what you get. Okay, so that's what the image of a set is. And if we want the formal definition, here it is. You take sets A and B, and a function from A to B, and a subset of A, and then you ask what's the image of the set E under the function f, and it's just a set of places you can get to in the, you see, where can you get to in B if you start in E? So one of the ways of saying that is all the values f of x you can get where x is in E, and the other way of saying it is it's those y in the codomain that you can get to from somewhere in E. And if you apply f to the whole of A, that's the image of the function, and that's also, as I say, which is the range of f. In calculus. So it's not a new concept, except about the only thing that might be new here is that you might not be used to applying it to subsets rather than to the whole thing. So as it says here, you might use the term range, but in Cambridge, I think they generally use range to mean the codomain, which is different. The codomain we had here, the codomain was R, the image was just the non-negative real numbers, and now the range depends on which version of range you're using, because if you mean codomain, it's going to be R, and if you mean image, you're going to get this one. So different people say the range of different things. But as long as you know what they mean in calculus, that's the main thing. Okay, so this notation f of E, f of A, and so on is very slightly misleading because this isn't the same function as before. We started with a function from A to B, and if you took an element of A, the result, you applied f, you got an element of B. But now we're trying to apply the same function to a subset of A, and to get a subset of B, which is different from an element. So it's really a new function that you got using the old function. And so if you want to know officially what's going on, we've got a new function that goes from the power set of A to the power set of B, where you start with E as subset of A, and then you do f of x, x in E, and that gives you a subset of B. And so this is a function where the argument is a set, and the value taken by the function is a set. But almost everybody still writes it f of E. But if you did want to write, if you want to distinguish it, you can write f of square bracket t. I've seen people do that. Just to remind yourself that it's not exactly the same as the old function. It's now, this is a new thing we're doing. We're taking a set and applying a function to every element of it to get a new set. Most people don't do this, but I have no objection. Okay, if you want to remind yourself that there's something slightly different going on here, you can use the square bracket. That's fine. Now that's what you call the image, or the sort of forward image, when you apply a function to a set. But the other thing you can do is try to come back. Now, of course, if you had an inverse function, you can come back just using the inverse function, and you do exactly the same thing using the inverse function. But what do you do if your function doesn't have an inverse function? What if your function isn't a bijection? I mean, we haven't really dealt with that much in this module yet. But what if you haven't got an inverse function? Can you still define preimage? And the answer is yes, we can. So let's first, for some reason or other, I'm telling you about reminding you about intervals here. I can't remember what this is for yet. But I want to remind you that there are a lot of interesting subsets of the real line. So when we look at examples, there are all sorts of intervals in the real line, which we looked at before. Okay, now the empty set and single point sets count as degenerate intervals officially. So the empty set is a rather strange kind of interval. The single point sets, like 2, you could think of that as the closed interval from 2 up to 2 if you want. Okay, so it's not too surprising that that's some sort of degenerate interval, but you can see that there's something strange about it because the endpoints are the same. That's a degenerate interval. There's lots of standard intervals that you know about by now. You've got sort of 0, 1, 0, 1, all the open intervals, closed intervals, half open intervals, unbounded intervals. R itself is an interval. These are very nice subsets of the real line. Q and Q complement are certainly not intervals. In R. The intervals aren't allowed to have gaps. Q has got gaps at every irrational number, not sizable gaps, but missing points, which counts. And Q complement has got missing points at every rational number. And they're all over the place as well. So these are definitely not intervals because there are... To be an interval, if you take any pair of real numbers in the set, everything in between should be in there as well. All real numbers in between are supposed to be in there. And that's how you characterize intervals in a sort of abstract way. Of course, you don't have to be that nasty. Even a union of two intervals that don't touch each other, well, 0, 1 union 3, 4 is definitely not an interval. It's a union of two intervals, but it's not an interval because it is missing some of the points in between 1 and 3. Sorry, not 1 and 3. 1 isn't in. But between 1/2 and 3, there are plenty of points missing, so it's not an interval. Right, so what is the preimage of a set? Interesting, in the exam last year, I asked for the definition of the preimage of a set, and essentially no one got it right. But then I asked later in that question for people to calculate the preimage of a set, and almost everybody got it right. They couldn't tell me what it meant, but they could calculate it, which was slightly revealing. Anyway, that was last year. What is the preimage or inverse image of a set? Now, what I want to point out here is this g to minus 1 is just notational because g doesn't have to have an inverse function. So this is a notation. It's on the notation sheet, and this is what the notation means. And like with any other definition, you just need to know what the definition means and how to work with it. So if I write g to the minus 1 of f, this is what I mean. It's those points in the codomain which are mapped into f. So you look at everything possible in A, and if g of x is in the set f, then you say, good, we're in the preimage. And if g of x isn't in f, you say, okay, we're not in the preimage. And that's a very easy decision to make, usually. So you can figure out what the preimage of the set is. Now, as before, you might want to use a square bracket because, you see, it is possible that g does have an inverse function. If g does have an inverse function, g to the minus 1 will have its own definition, and it will be a function. In which case, what we're doing here is slightly different, because this is now mapped from the set of subsets of B to the set of subsets of A. And again, you start with a subset of B, and you take the preimage, and you get a subset of A, which is those points of A which are mapped into F by G. I might draw you a picture in a minute just to clarify what's going on with all this. But for the moment, let me say, yes, that g to minus 1 is usually not... there are two problems with the notation. One is that g to minus 1 may not be a function at all on the original sets, but it might be because you might have an inverse map. And in calculus, you'll have done some inverse functions by now. And so you might have an inverse function, but even then, this is different because I'm applying it to a set instead of to points. So if g does have an inverse function, then this is just like the image that we had before. Instead of being a function of the elements of B, it's now a function of the subsets of B. And something interesting happens here. The preimage of the codomain is always equal to A. Why is that? Because the definition of g to minus 1 of B is equal to, by definition, it's those x in A such that g of x is in B. But g is a function from A to B. If g is a function from A to B, then that means everything in A is going into B. So x in A, so g of x in B is going to be everything in A. G of x in B, by definition of g being a function from A to B. So something a bit funny happens. This doesn't work for image. Preimage is actually better behaved than image is. The preimage of the codomain is always the whole of the domain, no matter what the function is. Even if the function is constant, if the function is constant, the image of the function will have just one point in, unless it's the empty function. So generally, the image of a constant function will have just one point in, and that's usually not the whole of the codomain. But the preimage, even if you have a constant function, is still the whole of the domain. So that's already a difference. Now on question sheet, on one of the question sheets, I can't remember which one, you get asked to have a look at image and preimage and try and distinguish their properties. And the properties of preimage are better than the properties of image, which means that there are one or two things that go wrong for image that don't go wrong for preimage, as you'll find out when you work them all out on the question sheet. Right. Now, so my first question then is to work out something about the preimage of this set, but I'm going to give you a little bit of help, okay? I'm going to remind you what x cubed minus x looks like. The function y equals x cubed minus x looks something like this. And you'll be asked, how many points are there in the set preimage of this two-point set? And again, I'll just remind you what that means. F to minus 1 of 0, 10 is equal to those real numbers, x in R, such that f of x is either 0 or 10. Okay? So you have to figure out how many real numbers have the property that f of x is either 0 or 10. And that's your task here. And I will let you think about that for a minute, and then we'll see how you got on. I'll pause the recording there. $22 answers so far. Okay, let's see what people have gone for. 26 answers so far, going up, and you can see we've got a majority going for C. Most people say that there's 4 points here, and that's correct. Though not very many of you answered the question. Okay, so the question is, how many real numbers are there so that f of x is either 0 or 10? Right? Now, I've shown you the 3 where you get naught. And we know that's minus 1, naught, and 1. And those are the points where f of x is equal to naught. It's not so obvious where f of x is equal to 10, but the main thing is, with 10 being up here somewhere, you look at the horizontal line and ask, how many times does it cross the curve? And it's well out of range of this region where there are several solutions. You see, there's a bit in here. There are some bits in here where the horizontal lines cross the curve multiple times. 3 in this range. The couple of places where it just touches the curve twice when you get it tangent to these things. So if you go just along the top of that hill there, you'll get a place where a horizontal line touches the curve twice. Once you get higher than that, and you can prove that 10 is higher than that, though I haven't given you the details, there's only one place where you cross the curve, and that gives you one more solution. And you can find that, certainly numerically, not so easy perhaps to find the exact solution. But those are the 4 points you need, and the answer is there are 4 solutions, because there are 3 solutions to f of x equals naught. But there's only one solution to f of x equals 10. I'll let you find out where that point is numerically, or perhaps some of you can. There are some horrible formulae around for solving cubics, so you might have to go for one of those. But I'll leave that to you. Right. Any questions about that example? Okay, let's move on to composition of functions. So what happens when you've got a function and another function and you want to do the function of a function? That's like doing the chain rule in calculus when you want to then differentiate afterwards. And so you're looking at f of g of x or g of f of x. You know, sine of cos of e to the x. You start with some relatively straightforward functions and you build them up into a much more complicated function just by taking a function of a function of a function. Okay, and that is what we call composition of functions. And the formal definition of g composed with f, which means do f first and then g. You use this little circle symbol here for the composition of two functions. So you've got f is going from x to y, and g is going from y to z. And you could put them one after the other. So I could do x going to y, going to z. And I've got a function f going from x to y. I've got a function g going from y to z. And so obviously I can get from x to z by doing f first to take me into y, and then do g afterwards to take me into z. And that's what f composed with g does. Sorry, g composed with f. It's getting from x to z by doing f first and then g. You don't have much choice about it because you can't do g first because g isn't defined on x. So you have to do f first and then do g afterwards. But it gets written this way round because that's the way it works when we have our functions on the left. There's not much choice of it, because what we're doing is we're starting with x, and then we work out f of x, and then we work out g of f of x. And that means that g ends up to the left of f, even though we're doing f first. And you've done, I mean, like this one here. We started with x, then you work out e to the x, and then you work out cos of e to the x, and then you work sine of cos of e to the x. The one you work out first is the one in the middle, e to the x. And then you have to take cos of that, and then sine of that. So the one you work out first is the one that's written further to the right. Here's an easy example. if you have polynomial functions, you can they go from R to R, and you can compose them either way round, and you usually get different answers, but not always. There are some fun examples which work both ways round. But here we are. We can work out what these ones are. We're going to have f of x is x squared plus 3, g of x is x minus 3. If I want to work out what f composed with g is, f composed with g of x is a function, so I have to know what it does to x. Okay? I'm putting the brackets round because it starts to get messy otherwise. So there's a function here called f composed with g, and I want to know what it does to x. Well, that just means f of g of x. That means, since f of x is x squared plus 3, f of g of x is g of x squared plus 3. Now, interestingly, I've done it this way. I've worked out, I've sort of applied f to g first. G of x squared plus 3. The alternative is to say it's f of x minus 3. So I could have also said it's equal to f of x minus 3. We're going to get the same answer. Okay. In either case, whichever way round you work it out, it's still x minus 3 squared plus 3, which is, I believe, x squared minus 6x plus 9 plus 3, so that should be plus 12. Probably. Okay? If you spot any mistakes, let me know. And now I'll try and do it the other way around. G of f of x is equal to g of x squared plus 3, but g of anything is that thing minus 3. So that's equal to x squared plus 3 minus 3, which is x squared, which is different. Okay? Oh, and that's g composed with f of x is g of f of x. So composing one way round is usually different from composing the other way round. So this is, although it sometimes gets used as a multiplication method, it's not commutative. So you have to watch out for that. It's a bit like multiplying matrices, really. Actually, it's very like multiplying matrices because matrices are rather like doing linear maps to things, as you'll find out. So, and multiplication of matrices turns out to be what you get by composing linear maps. So it's not only like multiplication of matrices, it's almost exactly the same as multiplication of matrices. Okay. But what we're going to finish with today is the fact that although it's not multiplicative, it is associative. And what does that mean? Suppose you've got four sets, 3 functions. So let me draw the setting we've got. We've got w, we've got x, we've got y, and we've got z. We've got f going from w to x, g going from x to y, h is going from y to z. Now, you can compose g with f to get a function from w to y. You could also compose h with g to get a function from x to z. And you can compose these composed functions with each other. So you could do g composed with f first to get you from w to y, and then you could do h afterwards to get you from y to z. Or you could do f first to get you from w to x, and then do h composed with g to get you from x to z. And that, which one you're doing depends on how you bracket it. But it doesn't make any difference. It turns out to be the same thing as starting in w, doing f, and then doing g, and then doing h. In fact, it's almost blatantly obvious if you think of it that way. all we have to do is start with a point in W, figure out what F does to it, figure out what G does to that, and figure out what H does to that. And they both turn out to be the map W goes to H of G of F of W, with unfortunately rather a lot of brackets. How many? 1, 2, 3, 1, 2, 3. That's what you end up with. But let's just see what a formal proof would look like. So the formal proof, to show H composed with G composed with F is equal to H composed with G composed with F, well, they've got the same domain and the same codomain Z. You can check that. So first note that they both have domain W and codomain Z. That's a good start. Now you have to check they've got the same graph, which means checking the values. So we just let W be W. Then G composed with F of W is G of F of W. That's the definition of the composite function. And so H composed with G composed with F, what does that do? That means do G composed with F first and then do H. So I have to do H of whatever G composed with F of W is. So that's simple. That's H of G of F of W, like I said it was. All right? Because I do H, I apply H to whatever G composed with F of W was. That's this one. But the other one is, what is H composed with G composed with F of W? That's H composed with G of F of W. Because this one, you have to do F of W first and then apply H composed with G afterwards. But to work out H composed with G of F of W, you have to do H of G of F of W. So this is by the definition of H composed with G, and that's the same as we had above. Equals, that's the same as the other one. So these two functions, whichever way around you work it out, they've got the same values at all W and W. So now we show they're the same function. Okay, any questions about that proof? All right, then we'll stop there and we'll start the workshop at 4 o'clock.